if that makes sense. Yeah, okay. So let's say, for argument's sake, okay, let's say an example, okay. The example is if we have five people, okay, so they're all unique, okay. So if we have 5 people, okay, and we want to make a committee, okay, of, let's say, 3 people, okay. How many ways, okay, can this be done? Okay. So if you think about it, we have 5 people. I need a committee of 3 people. Yeah. So I could take the first person, the second person, the third person. Yeah. I could take the second person, the first person, the third person. But actually, that's the same committee. Yeah. Okay. So the order doesn't matter. The order, irrespective of the order, and this is what's known as a combination. Okay. So actually, the total number of objects that we have is 5. The number of people that we want, the number of objects we want to select from it, okay, is 3. So actually, the answer here is 5C3, which is simply 5 factorial divided by 3 factorial times 5 minus 3 factorial, which gives us 5 times 4 times 3 times 2 times 1 divided by, well, 3 factorial is 3 times 2 times 1, and 5 minus 3 is 2, which is 2 factorial, so that's 2 times 1. Okay. The 3 times 2 times 1 goes with the 3 times 2 times 1. 5 times 4 is 20, 2 times 1 is 2, 2 into 20 gives us just 10 possible ways of actually doing that. Okay, if that makes sense. Okay. But there are rules. There are 5 counting rules. Let me just reflect back over them again really quickly. Okay. These are our 5 counting rules. Let me just get them up here. Okay, where's my other counting rule gone to? Counting rule 1. This is my counting rule. Here we go. Counting rule. This is my counting rule number 1. So let me just reflect back over these here. Okay, just a long old video. Okay. So counting rule number 1 says that if you make n selections, if that makes sense, okay, so if you take out n objects, okay, and that each time you make a selection, if the same number of objects are there for each selection, in other words, there's k objects, okay, that the total number of ways that you can actually arrange those particular outcomes, if that makes sense, or the total number of possible outcomes is equal to k to the power of n, where k is the number of objects, the same number of objects that you have on each one of the trials, and you make n selections from them. That's rule number 1. Okay. Counting rule number 2, okay, counting rule number 2 says if you have k1 different objects for the first selection, k2 for the second selection, and k3 for the third selection, and kn for the nth selection, well, then the total number of possible outcomes, okay, is equal to, well, how many possible things could you select for the first one? How many ways could you select for the second? How many ways could you select for the third? And so on and so forth. Now, this is a change to our first rule. The first rule sort of had a constraint on it where we had k objects. We had the same number of objects for each selection. Now with the second rule, what we're saying here is this, is that we have different number of objects for each selection, and that if you make them n selections, that the total number of possible outcomes is simply the product of all the possibilities, okay, for each one of the individual selections. Then we have counting rule number 3, counting rule 3, which is our factorial notation coming into play here. Okay, it's the total number of ways of permuting, let's say, permuting n objects. Yeah, so this is our permutation here. The number of ways that all n objects can be arranged in order. Okay, in order. Okay, so the order does matter. Okay, is n factorial. Okay. That makes sense. So if you have 4 objects, okay, well then the total number of ways that you could arrange them is 4 factorial. You have 4 choices for the first position, 3 for the second, 2 for the first, and 1 for the last position. And then finally, well, not finally, rule number 4 says, okay, instead of looking at the number of arrangements for all of the objects that we have, okay, say if we want to select a certain amount of objects from the total number of objects, okay, so what the rule says is permutations is the number of ways of arranging x objects, so this is the number of ways of taking x objects from a total of n objects in order. Order is important here, okay, in order is simply given by this formula here. It is, okay, the number of objects that we have n, the number of objects we want to select from the total number of objects, okay, it's equal to n factorial all over n minus x factorial. Order is matter. Order matters there, okay? And then the final one, which is a combination, says the number of ways of selecting x objects, okay? Once again, we're taking so many objects from n objects, okay? But this time it's irrespective of order. Order is not important, okay? Person 1, person 2, person 3, person 2, person 1, person 3 is the same. It's the same combination of people. Let's say, yeah, okay? It's equal to this particular formula here. The number of ways of taking x objects from n objects is equal to n factorial divided by x factorial times n minus x factorial. Okay, and there are 5 rules. So once again, guys, this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. I know this video is quite long, okay, but it does cover the 5 important rules when it comes to permutations and combinations. I hope that this was in some way intuitive, and more importantly, I hope that was helpful for you. And thank you for watching. Okay, bye bye.